Imagine you're standing in front of a furnace. As the metal inside heats up, it begins to glow. First a dull red, then orange, then brilliant white. This simple phenomenon, something humans had witnessed for thousands of years, was about to destroy physics. In the winter of 1900, every physicist in Europe knew that their equations predicted something impossible. According to the laws of Newton and Maxwell, according to everything they knew about energy and light, that glowing furnace should release infinite energy. It should explode. Reality said one thing, mathematics said another. And somewhere between those two truths, a German physicist named Max Planck was about to make a guess so desperate, so strange, that it would accidentally break open the quantum world. The question Planck faced was one of the great mysteries of the 19th century. When you heat an object, it glows. This is called blackbody radiation. And every star, every flame, every warm thing in the universe does it. Physicists wanted to predict exactly how much light and at what colours a hot object would emit. It seemed like a straightforward problem. Heat was understood. Light was understood. But when scientists tried to calculate the spectrum of light from a hot object using the laws of classical physics, the equations gave absurd answers. At high frequencies, the math predicted infinite energy. It was called the ultraviolet catastrophe, and it made no sense. Laboratories could measure the actual light from heated objects easily. The real measurements were smooth, predictable curves, but theory and reality did not match, and no one knew why. Before Planck, the world of physics rested on a foundation of continuity. Energy, it was believed, could take any value. It could be divided infinitely, like water flowing from a tap. You could have a lot of energy, or a little, and anything in between. This was the world of Newton and Maxwell, a world of smooth transitions and predictable mechanics. Waves were waves, particles were particles. Energy flowed continuously. It was elegant, and it worked for nearly everything. Pendulums, planets, engines, light. Classical physics had built the industrial age, but hidden in the glow of a simple heated object was a crack in that foundation. And Max Planck, a conservative and cautious man, was about to stumble into it. Planck was not a rebel. He was methodical, traditional, a man who believed in order. He had spent years trying to derive a formula that matched the experimental data for blackbody radiation. He tried every approach classical physics offered. None of them worked. Then, in October of 1900, he tried something different. He made an assumption. He assumed just mathematically, just to see what would happen, that energy was not continuous. Instead, he imagined that energy could only be emitted or absorbed in discrete packets. Tiny, indivisible chunks. He called them quanta. Each quantum of energy was proportional to the frequency of the light, connected by a single constant, a very small number. When he plugged this assumption into his equations, something remarkable happened. The formula worked perfectly. It matched every experiment. The curve fit the data exactly. Planck had found the answer, but he did not understand what it meant. The number Planck introduced is now called Planck's constant. It is approximately 6.6 times 10 to the negative 34 joule-seconds. It is unimaginably small. In the world of everyday experience, energy seems continuous because the jumps between quanta are so tiny we cannot perceive them. But at the scale of atoms and light, this number matters. It is the smallest meaningful unit of action in the universe. And its introduction changed everything. Planck himself called his solution an act of desperation. He did not believe energy was actually quantized. He thought it was a mathematical trick, a temporary fix until someone found the real answer. But the real answer was the one he had already found. Energy is quantized. The universe operates in discrete steps, not smooth flows. It was the birth of quantum mechanics, though Planck did not realize it at the time. At first, almost no one paid attention. Planck published his results in December 1900, and the physics community moved on. It seemed like a clever formula, nothing more. But a few years later, a young patent clerk named Albert Einstein took Planck's idea seriously. Einstein used it to explain the photoelectric effect, showing that light itself came in packets, in quanta, which we now call photons. Then Niels Bohr used it to explain the structure of the atom. Then Louis de Broglie, Erwin Schrödinger, Werner Heisenberg. One by one, the strange implications of Planck's constant forced physicists to accept a new reality. The quantum world was not optional, it was the foundation of matter and energy. Planck had opened a door he never intended to open, and the entire structure of physics walked through it. Today, Planck's constant is everywhere. It governs the behaviour of electrons in computer chips. It determines the colours emitted by LEDs. It is written into the uncertainty principle, which tells us there are limits to what we can know about the universe. It is part of the definition of the kilogram, one of the fundamental units of measurement. Quantum mechanics, born from Planck's desperate guess, is now the most successful theory in the history of science. It explains chemistry, condensed matter, particle physics, even the structure of stars. Without it, we would not have semiconductors, lasers, or MRI machines. We would not understand why the sun shines. Planck's constant is stitched into the fabric of reality. And it all began because one man, trying to solve a mundane problem about glowing metal, made an assumption he did not believe. Max Planck spent much of his later life uncomfortable with the revolution he had started. He never fully embraced the strange, probabilistic world of quantum mechanics. He was a man of order who had accidentally unleashed chaos, but that is often how discovery works. The biggest breakthroughs come not from grand vision, but from honest struggle, from trying every door until one opens. Planck found the smallest number in physics not because he was looking for it, but because he was willing to try something desperate, something that did not fit. And in that willingness to break his own assumptions, he gave us a new way to see the universe. Sometimes the most important discoveries are the ones we make by accident, and sometimes the smallest numbers change everything.